What's up, everybody? Welcome. Thank you for checking in. This is page 430 that we're working on right now, and it is a proof, and there's a lot to do. So I'm going to go relatively quickly through it. Please have something to write with, have something to highlight with, maybe multiple colors of highlight, because when we talk about a proof, and it's important for us in proof conversations to know what each of the pieces is referring to, some highlight color can help do that. Let's take a look at what this said. This is based upon what we did in the previous page. Go back and watch page 429 in case you haven't yet, just to make sure we're clear on what's going on here. In page 429, congruent chords are going to be equidistant to the center of the circle. We created perpendicular bisectors. We worked our way through the information on those problems in order to figure out that that was true. So here, let's highlight some things. Here's a hint. If they tell you there's a hint in a math problem, you better have that as part of your answer, because it's like they're giving you half of the work you need to do. They're looking for it. I'm looking for that from you in your response. So let's be looking for this along the way. Where is OE congruent to OI? And because it's something that we should focus on, let's bring in our highlight tool. Highlight is under the annotates. You should be annotating your book. You should be highlighting all over. You should be making sure that that book is useful for you. Highlight colors. And let's go OE and OI. Where are they? Well, there's OE and there's OI. We're trying to show that those two line segments are actually the same distance. Here's some things that we get though. So maybe bring in a different highlight color. CH is congruent to DR. So I gotta find CH and DR. CH is right here and DR is right there. So both of those are meant to be congruent to each other, and so that's why I've highlighted it this color. I think I'm going to keep highlighting blue, a couple more. So I'm going to highlight OE perpendicular to CH and OI perpendicular to DR, and that's actually showing up. Time for actually drawing in a little sketch right here. This is what they're talking about. That perpendicular box, the perpendicular box there and there, those two boxes are 90 degrees. It comes from these statements right here. Okay, let's prove CH and DR are equidistant from the center O, and that's where the green actually happens. So green is to show the proof. We better have at some point that statement come up. Okay, next up. Don't need this one. I don't need you. I need you to go away. I want to re-highlight this. Sorry, a little technical difficulty. Here we go. Add free highlight. There it is. Okay, scroll. Now, I do strongly suggest maybe like you pause right here, and with the video paused, write all this stuff down. Then I'm going to swipe up. See, I'm going to swipe up and show you more. There are 11 steps total. We're going to answer all 11. The first two are given to you in the book. Here's 3, 4, 5, 6, and 7, and 8. Pause. And you're back, I guess. So here's the remainder of the steps. Pause and write these down. And you're back, I guess. Thank you for doing that. If you are, if not, of course, you can pause at any time. Use the double speed. Speed me up. Make me sound like a chipmunk because I am talking so fast. But you're getting through the notes that you need, and we're going to explain how this proof works. Statement number 1. It's given. We already know that it's there. There's nothing for us to really determine if it's something that is important because it's been identified for us, and we highlighted this blue. So I'm going to go ahead and highlight that blue as well. It's already the blue from up above. Also, connect points OH, OC, OD. Oh, this is saying to do something that I haven't done yet. So I'm going to go up to, and I'm going to connect point O to H, O to C, O to R, O to D. I'm going to draw them in, and it's going to happen by something we call construction, which just means make it. So with our line tool, we're going to draw in the line. Let's draw in, I guess I'll use red. We'll draw in the line from O to H, O to C, O to D, and O to R. You should right now be thinking with what's been created, which shapes are those? And when we've talked about those types of shapes, we have some proofs that we can use. I mean, think about it. OH is a radius of the circle. OC is a radius of the circle. OR is a radius of the circle. OD is a radius of the circle. And when you have 4 radii lines, that one, that one, that one, and that one, and they're drawn in the circle, are they congruent? That's number 3. Those 4 segments are all radii of a circle. And the fact about radii of a circle is that all circle radii are congruent. Okay, that's what we say for number 3. That means then, you guys, that COH and DOR are congruent by the side triangle congruence theorem. Now that's a true statement because when you go back up and you look right here, this side, this side, this side, and this side, they're all the same length. And then way at the very beginning of this entire problem, we said that this line and this line, they're the same length. So I don't know if they're necessarily the same as the chord, but that distance, 2 spikes and 2 spikes, creates side, 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 matching side, 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 and so therefore the triangles have to be the same size. Triangle congruence. Once we know that triangles are congruent, the pieces of the triangle that we didn't talk about, we now know they're congruent. So if triangle COH is congruent to triangle DOR, then the angles in those 2 triangles are also going to be congruent. And so it's like after this statement, you always write CP, CTC. It's like they go together like peanut butter and jelly. They are matching in the problem. Now we have this one, angle OEH and OID. That's because we have up in our given, scroll please, we have this right here that says we have a right angle. We have a right angle, we have the definition of perpendicular. If you've been doing your Mathia, right? Amazing resource for helping us with geometry proofs. If you've been doing your Mathia, when some symbol was used, that symbol tells us the vocabulary word we're going to use later on. So this upside down symbol means perpendicular. And maybe you know that already, maybe you've never heard that before, but trust me, if you were paying attention, you've heard that before. So welcome to the rest of the world. The upside down T for us is going to mean perpendicular, and things that are perpendicular are actually forming right angles. Therefore, that angle, let's go spot it. It's right here, this angle, and also this one. I guess it's on the other side. It's over here like this. That angle as well. This angle as well. Those angles are 90-degree angles. Well, they're 90 degrees because they're right angles. And so therefore they have to be congruent because all right angles are congruent. Thank you, Euclid. That's a reference to the guy that wrote the first geometry book that we know of, right? He was the one that his book lasted for thousands of years. He said all right angles are congruent. Quote, Euclid. Okay. Since those right angles are the same, since they are created with congruent radii sides, created from the radii of a circle, that means that actually the triangles created by angle OEH and angle OID are the same. I'm going to say it's by side angle side. Is it side angle side? It's by hypotenuse angle. By hypotenuse angle. If you can find a hypotenuse, let's make sure you know what I'm talking about. This red line right here is a hypotenuse of this triangle. And then, no, wait, now I gotta go back and think about it for a second. It's hypotenuse leg. I'm sorry, I gotta go back for a second. I'm gonna erase that down there. The leg that they have in common is OE. Yeah. They don't have that in common, do they? What do they have in common? Go back and look for a second here. Definition of perpendicular, all right angles are congruent. The angle HCO and angle RDO, that's what it is. Okay, so I'm sorry, I just recognized that I have an angle and a side. So this is not hypotenuse angle. Sorry, back that up, back it up. I love having technology. I'm sorry that you don't. Hashtag also not sorry. By angle, side. So the angles, and then the fact that they have sides in common tells us that the two triangles, AO or OEH and OID, are congruent. So angle, side congruence theorem is what's doing that. Now, right after angle, side congruence theorem, we use what we say when we say triangle congruence. CPCTC. That always follows. Now, if those segments, OE, OI, where are they? Let's maybe get a highlight going on. Highlight these. Guess what? This is what I said to watch out for. It's happening right here. Highlight with green. There's this, and there's this. That's what I said we needed to look for, and they're happening right now. Those two sides are actually the same. They come from congruent triangles. Since the triangles are congruent, the sides that created them are the same. And then if they are congruent, they have to be equal. So a definition of congruent segments. Oh, come on now. I'm not sure I switched to red on or green on accident. Okay, definition of congruent segments. And then last of all, if the segments are actually congruent, then this is literally the definition of equidistant. It's right there in the statement. There we go, spell it right, equidistant. So therefore we're going to use it as our reason. These two side lengths are the same measurement. Therefore, they're equal. Definition of equidistance. The rest of this page's notes is on the equidistant chord theorem. It says if two chords of the same circle or congruent circles, so you can have them in different spots, but they're the same size, and the chords that are the same length on those circles or on the same circle, if they're congruent, they're equidistant from the centers of their circles. Centers of the circles. Maybe there's multiples. Let's conjecture that the converse of this theorem is also true. So we flip the order of this sentence. We're going to say it this way. If two chords of the same circle, or congruent circles, are equidistant from the centers of the circle, then the chords are congruent. Thank you for watching this video. This has been page 430. I have been your instructor for this video. The next part we're going to talk about is some application of the proof, actually. Page 431 is next. In that one, we're going to talk about the equidistant chord converse theorem. You are awesome. Thank you for watching this video. See you in the next one.